Hi everyone, welcome to the 2022 Asilomar Conference on Signal Systems and Computers. I'm Mahmoud and I'll be presenting our work on the distance geometry problem. So the distance geometry problem, or DGP for short, involves determining the locations of points in Euclidean space given measurements of the distances between these points. For example, in the figure on the left, we may be interested in recovering the locations of the points in this 2D structure given measurements of the pairwise distances between these points. So some of the applications of the DGP include computation biology, where we may want to estimate the locations of atoms in a molecule, such as the protein on the left, using the pairwise distance measurements. Another application is in wireless networks, where if we have an array of sensors, we can estimate the relative locations using pairwise distances between them. And then finally, in the robotics, if we can model a robotic movement using a pair of rigid bars flexing along a joint, we may want to determine whether these bars can flex to a specific point in 3D space, and solving the DGP can help us do so. So I'll use an example to describe what the DGP consists of, and the example structure on the left is what I'm going to use. So the first component is the set of points x1 through xn, and these points lie in k-dimensional Euclidean space. In the example on the left, this is R2, and there are 3 points, x1, x2, and x3. Between these points, there are edges, and that's shown in red on the left here. And then for each edge, we can determine its length using the distance function dij. And then finally, for each edge, there's an associated set of measurements. And given these components, we can, the objective is to determine the ground truth structure X, given noisy measurements of the edge lengths. Now, one thing I want to point out is that the measurements denoted by Y in the figure on the left are often assumed to be Gaussian. And in our work, we try to check the opportunity cost of using of this assumption, and we find that when this assumption is not valid, there is a large loss in performance. And I'll talk a bit more about that in a bit. So I'll just go through the process of how a structure is actually estimated in the literature. And I'll denote an estimate to be x hat and the ground truth structure to be x. So the common approach is, given the noisy measurements shown in blue for each edge, we first make an initial guess and compute the edge lengths, and this is shown in red on the left. We then compute the sum of squared errors, or SSE for short, between the measurements and the edge lengths that we just computed. And then we adjust the locations of the points to minimize the SSE cost function using, for example, a black box optimizer, which in our case is what we do, and which is actually sort of a strength in our work, because we can all we're doing is just modeling, and then we can use that model, we can put that model into black box optimizer, and then it gives us a result. And then we just repeat this process until convergence. Now note that the estimate has not converged precisely to the ground truth structure, and the reason is that there's noise in the measurements, so we can't exactly reconstruct the ground truth structure. Now I'll describe briefly what our work's been on. So minimizing the SSE cost function, which is often what's done in the literature, implies that the estimate would be optimal in the likeliest sense only if the measurements are Gaussian distributed. However, in practice, that may not be true, and that's what we're addressing. And in fact, we find that if the choice of the cost function depends directly on the distribution of the noisy measurements, rather than just using the SSE cost function for all kinds of measurements, we find that we can achieve the same estimation error using approximately half the number of edge length measurements for each edge. And so before I go into our results, I'll briefly describe how an estimate is evaluated. And note that because we're computing the error between edge lengths as that's sort of our objective function. And because edge lengths are invariant to rotation, translation, and reflection, then we'll need to evaluate our estimate up to rotation, translation, and reflection as well. And I'll describe now how that's done. So the first step is to translate the estimate and the ground truth structure so that their centroids are aligned at the origin. And then the next step is to solve this optimization problem where we're trying to find an orthonormal matrix R, which represents a rotation and or a reflection of the estimate so that it's aligned as close as possible to the ground truth structure. And if we want to compare OPP losses for different structures with different numbers of points, then it's a good idea to normalize the OPP loss by the number of points in a structure. Now, just to give an audience an idea of what the OPP loss values represent, here's an example. So there are two structures here, one on the left and one on the right. The ground truth structures are denoted by the black circles, and as you can see on the left, on the right here. And then all the other markers represent estimates with their corresponding OPP loss values. Now note that the smallest OPP loss value is the closest one to the structure, to the ground truth structure. So for example, the yellow star markers, which has the lowest OPP loss, is the closest to the ground truth structure. Now our hypothesis was that if we choose a cost function that corresponds to maximizing a likelihood function, then we'll observe a better an improvement in performance over using the sum of squared errors cost function that's usually used in the literature. And we tested, so to determine whether this hypothesis is true or not, we tested this on eight triangles and 30 10-point structures in 2D space. And for our noisy measurements, we used the Laplace distribution or the non-standardized student's t-distribution. So our measurements followed either one of these distributions. And then we computed the estimates for these structures using either maximum likelihood estimation, where the cost function follows the distribution of the measurements, or using just the SSE cost function, where the cost function does not follow the distribution of the measurements. And here are our results. So I'll just explain what the results mean using the figure A on the left here. So the x-axis represents the amount of variance of noise in the measurements. So the variance decreases going to the right, and on the y-axis represents the OPP loss. And you can see that as the variance decreases, the OPP loss goes down, which is expected. And another pattern to see is, and before I go into that, one thing to note is that these boxes represent percentiles. The bottom representing the 10th percentile, then after that is 25th, 50, 75, and then 90. And we see that there is generally a 3 to 4 dB improvement in performance when we use the matched likelihood function that follows the matched cost function, that follows the distribution of the measurements. In this case, this graph was for the Laplace distributed measurements. So the red box represents the Laplace likelihood or Laplace cost function, and then the blue box represents the sum of squared errors cost function, or equivalently the Gaussian likelihood. And we see that in general the Laplace likelihood achieves a smaller OPP loss. And another important thing is that across like 5 dB difference, the red box and the blue box are approximately aligned together, which means that we can achieve almost the same performance using which means that the Laplace using the matched likelihood function can lead to robust estimation, more robust estimation. And we see a similar pattern in the non-standardized student T case. And then finally here we plot the difference between the OPP loss values. And note that a more positive difference means that the Gaussian OPP loss is higher than the matched OPP loss. So the more positive it is, the more it matches our hypothesis. And we see, of course, that there are outliers that do not necessarily match that in the negative regime. And in this case, we do the same thing for 10-point structures. So the previous plots were for triangles, and this is for 10-point structures. One thing to note is that all we did was just add more points and then put it into the black box optimizer. And this is the advantage of using a black box optimizer. And again, we see a similar pattern. there's a downward trend, and also the matched cost function achieves a lower OPP loss value in general than the mismatched or the Gaussian likelihood function. And then finally, we want to see how the changing the number of measurements per edge affects the performance. In this case, we're plotting the median OPP loss rather than the distribution of OPP loss. And we're adjusting, for each line, we're adjusting the number of measurements per edge. That's what the capital M here represents. And again, we're plotting either the Gaussian or SSC cost function and the matched likelihood, or in this case, the Laplace function, the Laplace likelihood function. And the same thing goes for the non-standardized student T distribution here. And we observe that for half the number of measurements per edge, we can achieve approximately the same performance. For example, if we look at the solid line here, m equal 100 Gaussian, it approximately coincides with the m equal 50 Laplace line, which means that we've achieved almost the same performance using half the number of measurements when we use the right likelihood function or the correct likelihood function. And then we see the same thing here for these lines as well. Now I'll briefly describe some possible future research directions. So one of them is that we assumed in our work that the measurements are independent. However, in practice, that may not be the case. After discussing this with some other authors in the DGP literature, we found that more often than not, the measurements are dependent. And another thing is that we may want to incorporate prior knowledge of other structures. So, for example, molecules. It may be the case that some edge lengths are just not physically possible, while others are. One thing to note about the first two research directions is that we could these can be easily, in our case, because we're using a black box optimizer, these can be easily incorporated. One more research direction is the number of measurements per edge. We assume that the number of measurements per edge are equal and that there's at least one measurement per edge. However, in practice, that may not be the case because it may be physically impossible to obtain measurements for a specific edge. And then finally, we could try to theoretically derive some relationships for the mismatch between the likelihood, between using the likelihood function, like the matched likelihood function, and the mismatched sum of squared errors cost function. And that's it from me. Thanks for your attention.